Thank you. Thanks for the invitation to join this conference. I think it's a very timely and very interesting topic really for us to discuss and talk about. So at a very exciting stage now with so many different efforts happening. So in my talk, I'll share a little bit on the works that I've done back at my PhD at Yale University on engineering new types of interactions or gates between bosonic qubits encoded in multi-photon states of superconducting cavities. And then towards the end, I'll also show a little bit about what we're doing now in my new group in the National University of Singapore, and how we plan to continue to explore these interesting non-Gaussian states and use them for, say, things like quantum computing and quantum simulations. Okay, so to start with, I think this is a very general way to motivate why we want to have such multi-photon encodings for qubits, is because that provides a pretty promising way to build a modular quantum computer that could be universal and robust. Okay, and the way we think about it is, instead of having monolithic chips with lots of two-level systems that each only represent a physical bit, we want to build small pockets of logical qubits.
Yvonne, you are muted.
Yes, I think it says the host actually muted me. So anyway, small hiccup. So we want these individual logical qubits to have some sort of quantum error correction capabilities. And if we're able to do that, then the next thing we want to do is to form some communication channels and ways to do quantum gates between them, and then wire them up into a network such that we can perform more complicated computational tasks on them. So you can see that this kind of vision is very similar to a lot of classical systems where we build small individual elements in a modular fashion into a larger network of more complex devices, right? So ideally, what we want to have in order for this to work in the quantum regime is, first of all, some form of quantum error correction, at least to the first order within each of the modules. We want to be able to do gates or apply some logic between the different modules. And then we want to be able to make sure that they are connected in some flexible communication channels. Okay, so this is the general ingredients that we need for a modular quantum computer. And I think to tackle the first challenge of quantum error correction, as well as the second one of doing gates between them, we have to think a little bit out of the box. We have to look beyond just simple two-level systems, but rather looking at high-dimensional systems that can be more efficient in terms of hardware complexity and control overhead. So this is the reason why we chose superconducting cavities as the medium for encoding information. And this is really for a variety of different reasons, and I'm just highlighting a few here. One is that physically they already possess some very good intrinsic properties, such as coherence, large Hilbert space, etc. And this is great because we can very compactly put logical information in a single piece of hardware, right? And they also offer basically fairly straightforward universal control capabilities by simply coupling them to a nonlinear SLR. So this actually provides quite a lot of knobs for us to tune and adapt the encoding choices using the same type of hardware. And finally, we also know that in the recent years, there's been many different types of encoding schemes that's been developed to basically tackle different types of error models and different dominant error sources. So this is also another advantage, that we're not limited to one specific type of encoding in this kind of continuous variable-based logical information encoding. So because of these interesting things, and here are just some references for the latest, with some of the latest developments in the various codes. I'm showing the Wigner functions here. They're not the most intuitive, but you can see that a lot of these are highly non-Gaussian states, that their symmetry property actually provides a very, very efficient way for us to track the error syndromes and make corrections on them. So the individual error correction is, something that's well underway in terms of being developed and perfected. The next thing we want to think about is then how do we do some interesting gates between, say, two or more of these logical elements, right? This is the focus of my talk, basically. And we'll look at the simplest system that consists of two such individual modules, each potentially encoded in one of these novel non-Gaussian states. Okay, and what we want to achieve when we engineer these interactions is basically three general things. One, we want it to be programmable so that we can change the gates without changing the hardware. The next thing is we also want it to be agnostic to the encoding so that we can potentially adapt the quantum error correction schemes based on the local error model. And finally, we want it to be as robust as possible so that we can actually make high quality quantum computation using this kind of devices. So in this talk, I'll focus on two types of interactions that we have developed. One is the simple beam splitter coupling. This is a bilinear operation that essentially allows us to do things like interference or a swap gate. And the next one is an exponential swap operation, which is something that allows us to deterministically entangle two of these elements regardless of their encoding choices. So let's look into the first one for the beam splitter. Right? The medium where we actually, the hardware platform where we actually implement this looks something like this, where you can see that there are two 3D cylindrical, 3D superconducting cavities bridged by a nonlinear element. Okay, so top-down view can be seen like this, where we have a single Josephson junction that couples simultaneously to both the A and B mode. And this simple device actually has all the necessary ingredients that we need to test out our new interactions. So we have universal control through the single junction transmon in the middle. We also have very good isolation between the two cavities, which really means that they don't talk to each other or there's no interaction unless we program the specific one that we wanted. And finally, we also have some flexibility to introduce some additional knobs if needed by introducing additional SLS. Okay, so this gives us really a convenient and flexible platform to test out the new gates and interactions we wish to engineer. So the first thing I want to point out before we move on to talk about the actual beam splitter operation is that in general, as long as we have a large detuning between A and B mode, we can ensure that they have very little intrinsic coupling to each other, right? Because when these photons stored in the cavities are detuned, they do not naturally mix with each other. But we also know that if we want to enact a coupling of some form, then we can use nonlinear frequency conversion to enable that. Right? And this borrows inspiration from a lot of different prior works, such as the quantum limited amplifier or various parametric processes in circuit QED, as well as quantum optics, which essentially uses the nonlinearity of the Josephson junction to allow the frequency conversion to take place, given the appropriate microwave drives. So in this case, what we care about, is a beam splitter operation, which is sort of a bilinear coupling that's, swaps the excitation from mode A to mode B and back. So what this requires us to do is to supply two drives that exactly compensates for the energy differences of the two modes that we wish to couple together. And if we do that, if we use this frequency matching condition, we can actually engineer or introduce a new Hamiltonian term that's not present in the standard circuit QED system, right? And you can see that this term gives us the desired dynamics, which basically allows the excitation to go from A to B and back to A in a coherent way. So very intuitively, we can represent this in the single photon picture. And if we turn on the coupling, this photon should just coherently oscillate back and forth between the two modes, right? And experimentally, we can probe this quite easily by just measuring the joint probability of whether we have something like A in Alice in 1 being 0 or Alice in 0 being 1. Okay, so the first trace we show here is the probability of having one photon in Alice, but none in Bob. And you see this is a very well-defined periodic oscillation. And if we look at the reciprocal case where we measure 0 in Alice and 1 in Bob, we see that it just oscillates exactly out of phase with the same period. And overall, there's a decay envelope that basically tells us with some time scale, we will lose this photon regardless of the interaction, right? Because these cavities have the finite lifetimes. One other thing I would like to point out here is that you can see the x-axis here, the y-axis here doesn't go from 0 to 1 exactly, it goes only up to about 0.8. And this is a limited detection efficiency, which means just in our pulse sequences, our measurement ancilla is a little bit imperfect. And this is a very, an artifact of this particular device, not a built-in feature of the interaction at all. Okay, so this gives us a good indication that, if we just use this simple 4-wave mixing, we can turn on a beam splitter operation like this, and we can swap the excitation back and forth between two otherwise isolated cavities. And that's pretty neat, but this is quite limited, right? It's a single photon going back and forth. It's not exactly the most interesting thing to observe. So what we want to do is to actually look at some special points and see if we can actually use this new interaction to do something a little bit more complex and a little bit more exciting. So 2 specific points we identified one is the swap operation, which is the exact transfer of that excitation from one mode to another. And the other one is halfway between the initialization and the swap, which is a 50-50 beam splitter. Okay, so with these two, we can actually start to think about things related to maybe more interesting multi-photon states. So the first, I guess, starting with the simplest case is if we start in vacuum in one mode and a superposition of 0 to 4 photons in the B mode, and we turn on our swap operation, what we should see, or what we do indeed see, is that we have a complete transfer with the phase of the state of the initial state being fully preserved. Okay, so this tells us that the gate that we engineered indeed has two of the properties that we really want. One is it doesn't really care whether you are using a single photon or a superposition of different photons. So it's code word agnostic in terms of quantum error correction for eventually. The next thing that it manages to achieve is that he fully preserves the phase coherence in all the superposition states that's stored in these cavities, right? So this makes it a lot more useful compared to only being able to swap a single photon back and forth. The next thing we want to try is, can we use this beam splitter to do some interference experiments? So I think, as we all know, the Hong-Ou-Mandel interference is one of the most classic signatures that we want to observe in quantum optics. And we do exactly the same here, right? We just put in 2 excitations, one in each mode, into our engineered beam splitter. So normally it shouldn't do anything because these 2 photons are detuned. But because our beam splitter provides the full compensation of their detuning, we actually allow their interference to take place such that we either get 0-2 or 2-0 at the output. Right? So if we were to measure this dynamics, what we observe is that the color bar, the z-axis here, is the probability, right? For 1-1, we start with high probability, but after a single beam splitter, we actually reach a equal probability of being in 0-2 or 2-0. And this is what we expect. But just looking at this alone, right, because we're only looking at probability, we can't really tell if their relative phases are well preserved, whether 0-2 plus 2-0 or minus 2-0, or is it a mixed state. We can't tell at this stage. But what we could tell, though, is the fact that at the next beam splitter, it fully reconverges back to 1-1. And just by simple back of the envelope calculations, we can tell that if there's no well-defined phase, then this re-emergence of the 1-1 peak after the second beam splitter will not be possible. So this gives us a very good indication that we have a coherent beam splitter that could bridge the 2 different frequencies. Okay, and this is very useful in terms of studying quantum interferometry, but it's not the most useful thing in terms of logical operations for 2 reasons, right? One is the fact that we're no longer in the original code space, which is the 0-1 subspace, because now we escape to 2, right? So in terms of encoding and decoding, not the best. And the second thing is that while we do have a highly non-classical state, right, of 0 to a NON state here, the non-classical feature really comes from the fact that we put in two Fock states, which are themselves non-classical. It's not really due to the operation itself, right? So this is, in some sense, not a code agnostic quantum operation. Okay, and to verify that, we simply just use a different kind of state, right? So here we, instead of putting in two non-classical states, we put in vacuum and a semi-classical state. And we go through the same operation, we see that there's no longer non-classical features emerging, right? So this is something intuitive, but I think it's always good to for when we were doing the experiment, it's always good to remind ourselves that what we engineered is a bilinear operation that doesn't deterministically entangle the modes if we put in semi-classical states. Okay, so this actually gives us the motivation to move further beyond this and actually build something that could indeed deterministically entangle regardless of what initial states we put in. So, but before we move on to that, I just want to show that, you know, even though it's a simple beam splitter operation, it is still a very useful thing for things like quantum interferometry. Earlier I showed the Hong-Ou-Mandel interference, and here I'll show the Mach-Zehnder interferometry that we can set up using the same operation. So in a simple Mach-Zehnder, what we aim to do is to have two beam splitters, and we put in a variable phase to see the resulting state, right? So if we perform this in our hardware, what we see is that we can start in 1, 1, and you will go to A equals superposition of 0, 2, and 2, 0, if there's no additional phase. But now if we introduce the phase using our natural dispersive Hamiltonian, which is basically an evolution of this coupling term for a period of pi over chi, what we see is that instead of reconverging back to 1, 1, they're somewhat frozen in the subspace of 0, 2, and 2, 0. Okay, and this is very interesting because you can think about this as, you know, in some sense, that we are making this, the bosons in our superconducting cavity a little bit like fermions, right? They no longer want to be, they no longer want to obey certain symmetries, but rather they would stay in the other configuration. Then the next thing we can do is to reverse this process by introducing another pi phase shift on one of the modes. And what this does is that it now changes the dynamics fully again by allowing the reinterference of the 1-1 combination. And if then we let it evolve naturally on its own under the beam splitter interaction, we see the recovery of the standard Hong-Ou-Mandel interference. So this is something quite useful because all of these little ingredients are already present in our circuit QED hardware, and we can do this on the fly. Right, so we didn't have to change or reconfigure anything in our hardware. We simply enacted certain gates at the right times, and this would allow us to change exactly what kind of dynamics we want to observe or want to achieve in the interferometer. And this programmability, I think, is a very useful feature for this kind of microwave activated interactions between bosonic modes. So here there are some additional features that I would like to point out. They are consistent with decoherence between the two cavities. So as we continue the evolution, we'll start to lose photons from either one or the other cavity. And here we see the traces starting at really low points, but starting to peak up as time goes on, corresponding to either omega 10, omega 01. So basically one of the cavities losing a photon or from the other, or both of them losing the photon as we go towards later times in the evolution. Okay, so the next thing that this particular type of interaction is useful for is actually in terms of the extraction of state overlap, or basically a single bit of information that we can effectively get if all we want to know is whether two quantum states are the same. And this is done in the atomic physics community quite a lot. And effectively, it uses quantum interference and the symmetry resulting from that to say that if the two states are the same after they interfere at the beam splitter, then the resulting state should always be even. And if they're different, then we should only get the odd combinations. And this feature is very useful because very convenient for circuit QED, because parity is something that we can measure very directly in our system. And how do we achieve that, or how do we verify that, is to initialize our two modes in, say, two coherent states, one with a fixed phase and one with a variable phase. Okay, so just naively, we can already see that if the size of the coherent state is the same, we'll only get the full overlap or the identical, the answer of these two states being the same, what phi A is the same as phi B. So, so let's try that in practice, and we initialize the states. This initialization is very simple, just a simple displacement in each mode. Then we turn on the engineered interaction, the beam splitter interaction. And we use our natural dispersive Hamiltonian and the series of simple gates to perform a parity map onto our ancilla. And with this, we can basically track the overlap between the two states as we sweep the phase of one of the modes. Okay, and we see that as we change this phase, we periodically achieve either either even or odd parities at exact locations that corresponds to the two phases being identical. So this is what we would expect to see intuitively. We can also verify this for different displacement sizes. So imagine if we push the two coherent states out further together, then this overlap gets narrower and narrower because it becomes more and more sensitive to the small mismatch between their phases. And this is indeed what we observe as well. Okay, so another demonstration of the usefulness of such an engineered beam splitter operation in this case. So we've talked a lot about the beam splitter and what we can use it for, but one thing I've alluded to earlier is that it's still a bilinear operation. It doesn't give us any deterministic entangling operations, which is very crucial and which is necessary really for quantum information processing in general. Right? So now let's move on to think about the second case, the second gate that we constructed, which is called the exponential swap operation. How do we think about this intuitively? Well, the way I like to think about it is the exponential swap gives us a way to build a superposition of fully swap and not swap at all, right? And if we do this, we effectively have a way to always entangle the two modes that we're swapping between, regardless of what's encoded inside those modes. So mathematically, this will look something like this, where we have a tunable mixing angle, that weights the identity and the swap operation. And as we tune this angle to certain specific values, we'll get a superposition between these two operations, or either one or the other. Okay. So from this form, it also is very apparent that this exponential swap unitary always entangles the two modes, regardless of the initial input states. And that's a feature that we really want for our hardware to have. Okay. Another thing, in general, this is a useful gate also because it forms a universal gate set together with some single unit control, a single mode control. So this is useful in terms of the general universal algorithms that we want to perform on these modular devices eventually. It also has some other applications, such as quantum machine learning and quantum principal component analysis. So it's overall a rather useful gate, and I think it hasn't really been explored that much prior to our work. There has been quite a lot of interesting theoretical work, but experimentally it has been a little bit difficult to realize. But for us, we've shown that we have essentially all the ingredients to do a good swap and identity is very simple in our system. So the next thing is to figure out how do we then introduce this programmable weights to form this coherent superposition between identity and swap. Okay, and the sequence, as proposed in the original paper by Lau and Plenio in 2016, is that we use two Fredkin gates sandwiched by a single mode rotation on one of the ancillas. So this is conceptually quite straightforward, but Fredkin gates are three-mode operations that are quite difficult to implement at high fidelity. So to bypass that challenge, or to maybe circumvent some of the challenges, we actually came up with a way together with Liang Jiang and Steve Irvin to decompose a Fredkin gate into something a little bit simpler and more natural in our system. And this is basically shown here, where a single controlled swap gate can be broken down into two beam splitters with opposite phases, sandwiched by a controlled phase rotation. Okay, so this controlled phase rotation is exactly what we used before to map parity. So this is a natural gate because of the dispersive interaction, and it's very easy to implement. And the beam splitter operation is what we showed earlier in the interferometry applications, where we can engineer this bilinear coupling between the two modes. Okay, so once we do this particular decomposition of the Fredkin gate, this the exponential swap operation becomes a lot more viable in our system. And what we could also do is to play some tricks in the order of things, because some of these operations commute with each other, to simplify the overall circuit as well. Okay, and the final circuit looks something like this, where we have our two modes, each encoded in some chosen state. Here I even used the density operator to show that they don't even have to be a pure state, right? So they really can be any general state. And a single ancilla is involved in this operation. And we effectively have to perform two beam splitter operations. And in between, we have several single qubit, single ancilla, as well as controlled conditional gates between the ancilla and one of the cavity modes. So all of these single ancilla operations are fairly fast. So overall, the gate time is favorable compared to the coherence times we have in our system. Also, the ancilla itself starts and ends in G, so that gives us a way to basically alleviate the decoherence penalty imposed by the ancilla. Finally, we can also think about how to improve these beam splitter operations. For this implementation, they're about 5 microseconds each, but thankfully they're slow. Despite their relatively long gate time, their quality can still be high, because at this point, only the two cavities are involved, and both of the cavities have much better intrinsic coherence compared to the ancilla mode. So with these in mind, and just the final note is that all of these single and conditional single ancilla rotations and controlled rotations are basically results of the natural dispersive interaction. So they're fast and relatively easy to implement. Okay, so this whole thing we can put together using our existing hardware without further modifications. And now what we're left to do is to test it out, right? If we implement this circuit, then we can put in some initial state of choice. And in this case, we just choose the simplest one, like alpha and minus alpha, because they are semi-classical, first of all. And if there's any entanglement at the end of the sequence, then that is a result of our operation rather than the non-classicality propagated from the initial state. So what we expect to see is a two-mode entangled state. We have alpha plus minus alpha and the complementary combination with the opposite phases. And because it's a two-mode entangled state, we actually have to use a four-dimensional Wigner function to capture its signatures. So instead of plotting a four-dimensional hypercube, we shows two representative plane cuts to show their most prominent features. So one plane cut is along the imaginary and imaginary axis of each mode. And we see that the only features there are basically represented by the interference fringes. Okay, and this is a highly non-classical feature that we expect to see if we have entanglement at the end of this operation. In the other plane, so fully orthogonal to this, we have the real and real plane. And in this cut, we see that we should only see the distribution of the population. And in this case, since we have two coherent states, we see that the probability of measuring any population, photon population, corresponds to where the two coherent states are. So this is a direct calculation of what we are expecting to see if the operation were to be successful. And experimentally, this is what we observe. Okay, you can see that the fringes reproduce really well what we're supposed to see in the calculation, with some small distortions. Okay, but this distortion becomes a little bit more obvious in the other plane, the real and real plane. Right, we see the population distribution, but we see some faint fringes in between as well that shouldn't be there. So this got us thinking, like, could there be some higher order effects in our system that we haven't accounted for in our naive calculation of the ideal outcome? And once we take that into account, so the higher order nonlinearities of the two cavity modes, which is basically their self curve, we actually reproduce these additional features quite well. Okay, so this tells us that we have indeed engineered an operation that gives us the desired output state, and all the additional features are consistent with the presence of higher order Hamiltonian terms in our system. The next thing we try to do is to think about this in the subspace, think about this as two logical bits. Okay, one of them, let's say we think about them as 0 and minus alpha as 1, then we basically have a 2-qubit register. And what we can do is to measure their Pauli correlation, their two-mode Pauli operators, and use that as a gauge to quantify their entanglement as well. And in this case, we see that the grayed out areas are the simulation, with some imperfections, such as the higher order nonlinearity taken into place. And the colored, solid colored bars are the actual experimental data. This is all raw data without any post-processing or normalization, but you can already see that qualitatively, they reproduce the signature extremely well. Okay, and what we see is that indeed the distribution only fall at the few Pauli operators where we have the joint probability representing entanglement, and then the identity, the II and ZZ operators corresponding to the population distribution. Okay, we can also use this as a way to quantify the overall performance. And what we see is that without any correction of the spam errors or the known decoherence errors, we effectively can get a 74% overlap. And this may not sound very high, but we do know that in independent calibrations, we know that out of that, quite a fair bit is from the detection, because two-mode joint Wigners are not exactly easy to measure. So there's a big chunk taken out by spam, but thankfully, the comforting part for this other, the remaining 10% of the fidelity reduction are all very well accounted for by the non-idealities that we understand quite well. So in terms of sort of leading to the leading order, we have the Kerr effect, so the higher order Hamiltonian terms that come into play. And then we run into things like cavity relaxation, decoherence, and some induced imperfections in the engineered beam splitter. But this effect, which is really what we care about the most, is how good our operations are. Unfortunately, we can't extract that without the others very accurately. But we know we can place a bound on this from independent calibrations, and we know that this is definitely not a dominant error at this point. Okay. Next, we can look into this full unitary again, because so far the only thing I've shown you is two very selective values of theta of our tunable mixing angle, right? So what if we actually tune this dynamically as we implement the operation? Do we actually recover the entire unitary? Well, to answer that question, we actually performed the experiment by sweeping theta over a full period. And what we see is that the 2-qubit Pauli operators have the correct signatures as we would expect. For instance, the ones that corresponds to the populations do not vary as a function of theta, because they should always be conserved. But the ones that corresponds to the parity or the correlations would actually start to oscillate. And we see that as special values of, say, 0 and pi/2, we've done a full swap, for instance, and at minus and plus pi/4, we have full entanglement, as characterized, as indicated really by the joint 2-qubit operators that have their peaks at these two values. Okay, so this basically demonstrates that we have indeed not only access to the special instances of this particular unitary as gates, but we also have the flexibility to tune exactly what gate we implement in a very programmable fashion. Okay. Lastly, we can also perform some more advanced tomography techniques to just put perhaps a more stringent metric on the quality of the eSWAP operation at various different angles. And you can see that from these process tomography patterns, we generally qualitatively reproduce what we're supposed to see with some small imperfections. The useful thing from these data is that we can start to look into these individual spurious populations and their phases and use them as diagnostic tools to help us improve our operation in the next iteration. Okay. We also tried this on several different encodings to show that they're indeed agnostic to the choices of encoding. So we tried coherent states, 0 and 1 Fock state, as well as binomial state encoding. And we see that on average, we get about 65 to 75% fidelity without any corrections. And with corrections, this goes up to about 80 to 90% in fidelity. Okay, so based on these few pieces of results that I've shown so far, I think what we can conclude is it is indeed possible to implement this type of programmable interactions between two otherwise fully isolated bosonic modes, and this is quite a useful thing for performing quantum algorithms and quantum computation on this type of continuous variable based logical qubits. We also know that there is some small imperfections introduced by the simple 4-wave mixing in the single Josephson junction, and this potentially can be improved if we use more specialized mixing elements, such as, say, a snail or other configurations with multiple Josephson junctions. Then towards the goal of building a modular network of these individual elements and performing quantum error correction on them, we can see that what we implemented here can be easily generalized to larger modes, and this is useful for not just information processing, I would say, but also things like quantum simulation, which has been demonstrated a year after these results were published back at Yale by some of my teammates to simulate molecular structure, energy distribution. And also there's been some works on quantum metrology based on this type of continuous variable based multi-photon states in cavities. Okay, so that's all very exciting. And I think in my new group, we are going to continue to explore all the new and interesting physics that this type of states would offer us. And the way we think about it is that we can build architectures that look something like this to provide very useful and sort of versatile testbeds to explore these new physics. So this is a very naive cartoon of what we might be able to build, but effectively you can see the core features are the same, where we have several linear modes. Each of them can perhaps have their own ancilla and readout channels, but they can interact through some nonlinear mixing channels consisting of either single or multiple junctions. And we should be able to initialize any type of bosonic states, multi-photon states in them, and enact some different types of interactions based on the target application at hand, right? So this should be a relatively versatile structure. And everything here is modular because we can replace the chips without affecting the rest of the system, okay? And despite the past year, strange year of the global pandemics, we are well on track on building our infrastructure in the lab. We have, I think, our first devices just called right now to start our measurement. And yeah, we're really looking forward to continue to explore this very interesting branch of physics in circuit QED. So with that, I would like to just flesh out a few possible things we may want to do, like, for example, multi-qubit unitaries on these continuous variables, looking a little bit more into different ways of doing quantum error correction on them. Also think about, more different, more exotic kind of quantum states, such that we can explore different physics or use them to simulate or model different complex systems. Okay, and with that, I'd like to thank you for your attention, and I'll be happy to answer any questions.